last night took me a little bit longer. It's not like some of you took even longer. Okay, well today we're gonna be done before noon. I'm shooting for 11:30. And then at that point, if you wish, you can stay in here and take the test. You can go home and take the test. You'll have up to 7 days to take the exam. Once you start the test, the clock starts running for 3 hours. We'll go over a little bit more of that after the presentation. Before we dive into expansion joints, anybody have any questions about anything we covered yesterday?
How many steel bridge questions are on the test?
Not sure, probably 4, 5, something like that. Not as many as reinforcement. But yeah, there's some, but yeah, steel bridges are a little harder, but the questions are, I think, they're fair. Every year, actually, we check which answers have the most people that got wrong, and then we figure out, is there something with the question? Did we word the question or the answer wrong? And every year we're making some updates. This year we, on the week 1 exam, I think both weeks actually, we changed like 3 questions. Just because it must have been confusing the way they were worded or whatever. So give you guys a better chance to pass the exam. Any other questions? Okay, we've got Mark back again for expansion joints. So Mark will lead us through this one. Was it 11? Section?
Oh, I don't know.
But it's, you got the agenda right here. Yeah, tell the presentation.
Friday, 11. Yep. And manual section 11. Presentation page 1415. Yep.
So, anyway, if you want to. So, that, we'll go through this one, then we'll take maybe a 10-minute break, and then we'll have the list.
All right. Well, welcome to Friday. I hope this week was good for you. Again, you know, I'll say it again, if you have any questions, except for today or next Friday, somebody was going to try to call me today, from a friend, or while they're taking the test or something. But always feel that you can reach out to us. So, yeah. So I think today is going to be kind of fun. You know, we kind of saved some interesting stuff for the last day of the week. Birth, life, and death of an expansion device. We're just going to have some fun with this. Melissa Schultz is going to be right after me. She's going to be talking about aesthetics. She's really entertaining to listen to. So I hope it'll be kind of a relaxing day for you. So we'll go ahead and get right into it. The reason I put this up here is this is a cover plate, and this is put on the barrier. So concrete is barrier. If it's steel, it's called a railing. Okay, so a barrier, and it has to be in the line of traffic, the way the traffic is going, because if the snowplow comes here, and they usually use the barrier as a feeler for their plow blade, and sometimes they'll bump into this gently and ride it so that they know they're all the way over. But if this is reversed, and sometimes the contractor reverses, we get one probably once a year where they put the plate on backwards. And so now the expansion, this is fixed here, and it expands here. So there's an opening, and if that's on this side, that can become a snagging hazard for the plow. So anyway, that's why I have that on the front sheet. But what we'll share today. So what is an expansion joint? Why we have them? When we have them? The different types, standard plans. We'll go through some shop drawing review. The actual fabrication, we'll take you to the shop, and then to the hot dip galvanizing tank. We'll show you what that looks like. Some construction site, and then once the contractor's done with it, then it becomes ours, and maintenance takes over. Anytime you see this little dude pop up, that'll be a sign that we're going to have a question. I know you have the answers in your PowerPoint, but If you place every expansion device of every bridge in Minnesota end-to-end, how many feet of device would that be? Anybody want to take a guess? Is it a lot?
1.5 million?
1.5 million feet? Oh, I never looked at that. Well, that's pretty big. Anyway, 76 miles, so it's really literally about from here to Rochester if we were to stack them all next to each other. So it's a lot. Expansion joints are all around us, right? Because we have thermal expansion of every material. And we always put control joints. The last I heard from the concrete office is we tried to keep them at about 15 feet or so. That number changes all the time because of the concrete recipes. Railroad tracks have them. They call them a fish plate. Piping systems, you know, because it's gonna, and this one I thought was really neat. Big ships actually have them for flexing and expanding. So they are literally all around us. So Mr. Webster tells us that it's an assembly designed to accommodate the heat-induced expansion and contraction of construction materials. 4 expansion joint gaps were built into these structures. There were many cracks, stresses, right? We have some older bridges that move a lot. I know of a couple bridges up in Duluth that move their ramp that go up to mainline 35. And you think that gravity would make the bridge go this way, right? Downhill, it doesn't, it moves up. And the engineers will scratch their head for years on why, but we just accommodated and we figured it out. That bridge is moving uphill. What do joints accommodate for? So definitely temperature is probably the biggest one. Traffic, movement, live load, wind loads, you know, we get ice loads on bridges, shrinkage and creep. And sometimes we have to go out and maybe our bearing assembly has moved. We have some bridges that are pretty active. If you're familiar with 494, you go past the airport, you're going eastbound on 494, and you're going over the Minnesota River. Those 2 long bridges that go 9217 east and westbound is the bridge numbers. But they have neoprene expansion bearings, pads in there, and the bridge moves enough where the pad actually walks out underneath the bridge. So sometimes we have to go in there, maintenance will have to go in there, and they'll jack up the bridge, so now your expansion joint, so your bridge can come up and your abutment stays static, and we can move those bearing pads and bring them back down. So we have to have something in the bridge to allow us to jack it up. So why include joints on the bridge? Do all bridges have expansion joint devices in the superstructure? Does everybody say yes? Everybody say no? Everybody's gonna guess today? All right, we gotta do it again. Who thinks that all bridges have expansion joints? One person
In the
in the superstructure? Who says they don't? Everybody? Okay. So we have integral. You've gone through integral, semi-integral already, Paul? Yep. So you guys know what those are, single line of pile. Where's the expansion joint on that type of bridge? On the approach, right? So you typically would add a 20-foot approach panel, and we tie it directly to the abutment, and then as the bridge expands, it literally goes like this, theoretically. Okay? Semi-integral abutments, you sit on a bearing, there's a beam coming across, it's tied into this upper part, and the expansion happens right in here. Okay? And then slab spans are a rig of their own.
They don't have, those bridges don't have an integral or semi-integral on both ends, do they?
We have bridges that have one on one and one on the other. Yeah. Yep. Yep, we do. So here's a behind the scenes picture of an integral. You can see we put a little tiny neoprene pad underneath there. We put some foam underneath the front of that. And then this all gets filled in with concrete right around the beam end. And this allows the beam to rock back and forth like this. So, you know, the beam's going to flex, it's going to move. So we put a little neoprene pad underneath there, and then we fill it all in with concrete. That's what it looks like at the finished end there. So fixity is a term that the designers would use, and it means the point of fixity is the neutral point on the bridge that does not move horizontally. So everything is locked right in at that spot. So if we think of let's think of a two-span bridge. So we have one pier in the middle. Most likely that bearing would be fixed. So everything is going to move from that point out towards each end. Here's I thought it was a nice little diagram here. This a consultant had put this together, and I borrowed it to put it into the. So this is a semi-integral, and you can see that we're fixed out here at kind of the center. That's the theory again. So everything's going to be moving this way, or everything should be coming this way. So it's not necessarily fixed, but that's the point of fixing. On a semi-integral, you can see that this is labeled as a fixed bearing on this end, and then there's an expansion on this. So they kind of build this so that it's kind of locked in, and then all the movement goes this way. Here's your expansion joint out here at the end of the approach panel. We call that a sill, or we call, sometimes, you know, our generic term is a sleeper slab that we would build underneath, and that keeps the approach panel and the concrete main line from having some type of differential settlement like that. So that sill helps support. Okay, makes sense, everybody so far? Parapet abutments, those are the high abutments. A lot of times they'll have an expansion joint on each end. Okay? And we would still have an approach panel. We would still have another opportunity for expansion out there, because that's going to take up the expansion of the main line coming up to the approach. Okay? So we used to call them E8H, stand for expansion joint, and then this was 8/2, a 4-inch opening, and then the H was a hot 4, and then they changed, they added a 1 in there, and now we're back to an E8 or an E5. E5 is brand new in probably the last, well, March of 24. Is when it was introduced on the new approach panel standard sheets. So an E8 is a 4-inch opening. You can see that here. This is looking down. Here's the concrete approach here, and then there's the main line there. So we're going to fill this 4-inch opening with some type of a seal. And this is kind of the popular one. It's a foam. It's a real dense foam, and then it has a silicone top on it, which is the UV protection part. And then this is under pressure. It's squeezed right now. So if you cut this plastic off, then it starts to open on its own. And then put adhesive on the sides. It worked pretty well. Another opportunity is this is the DS Brown gland, and they fill these little ridges on the side with epoxy. And they smear epoxy on the concrete as well. On both sides, they push it down. This is the DS Brown JP 400, 4 inches. And they call it the JP because it's pedestrian, so it's flat on top instead of being a deep V. So when people, maybe if you know high heels or something like that, you're walking across, you want that to be continuous. So This is probably the Cadillac. This is be the next step down, but we look at them both as equals on the APL. Contractor's going to install most of the time the least expensive product that they can purchase, right? Since we're a low bid state. Okay, so everybody gets an idea of what this was the old, it was a piece of foam. I think it was about 8 inches tall, it was 4.5 inches wide. You put some lube adhesive on the side of the concrete, and you push that foam down in there. So it was about, I'd say about 1.5 inches below the driving surface, and then they put a hot pour on top of it. So that's what you see right here. That's the hot pour on top. Like a crumb rubber hot pour, what you would use in joints and stuff. All right. So this was the latest that I heard, bridges up to 340 feet. We can build without expansion joints on the bridge, so that again, it'd be semi-integral or integral. And I was going to mention, what does the E5 mean? That's a 2.5 inch. So we might have a really short bridge where we don't need a 4-inch opening. So they would come in and they would choose to put a 2.5 inch joint. When a joint opening, so let's say this is a concrete main line on this side, and that's opening up, maybe it's migrating away. When an opening gets to about 5 inches, we start to get phone calls. Because that's a pretty good, wheels are dropping into that, especially on motorcycles. Wheels are dropping into that, and people are recognizing, hey, maybe there's something wrong with this. Okay? So this is 371, I think, up by Fort Ripley, a bridge, and it's a integral bridge. So there's no joint, but there is a sawed and sealed joint there because the bridge is going to stay static, right? It's not going to shrink or not shrink, but it's not going to dip. But the approach panel is hooked to the abutment, but the approach panel might settle, right? Because we really don't have anything underneath that approach panel as a footing to keep it from settling. So we do put a sawed and sealed joint right where it meets the abutment. And in this case, since there's bituminous, would there be an E8 joint or an E5 joint in here? Typically not. Typically they just butt it right up to it. And then they maintenance deals with that, expanding and contracting. In the summer it might expand and get a bump there. Well, then the snowplow is going to come through in the fall or winter and take care of that. Yeah, so a little bit of a maintenance issue right here. Okay, so three main types. We have of joints depending on the amount of calculated movement. Okay, steel finger joints. And the finger joints is literally that. That's 2 steel plates, and they look just like your fingers, and they open and close like this. Okay. Then we have the waterproof. It's the single gland, and this is the steel flex. These pieces you'll see later when I take you into the shop. That these pieces are actually have extra big pieces of steel on them, and they're cast right into the deck. And then we have the SSA2 gland, and this is kind of the latest and greatest. So we've been using this one for a very long time. So different names for that. Some call them strip seals is probably the most common. Some people say strip steel, but expansion joint, single gland, strip seals, pretty common. And then we have the modular joint, and that would accommodate really, really big, long bridges. Let's say River Crossing had some massive ones in there. I don't know how many cells were those, Paul? 13 or something?
Yeah. Yep, 13 cells, 39 inches of movement.
Had accommodate for 39 inches of movement on that bridge. So here's a picture. This is Interstate 94 near Fargo, Moorhead, going across the river. And you can see there's that finger where the lights come through up here. That's that finger joint. Okay. But what happens at that finger joint is everything comes through there. It doesn't go off the end of the bridge. So we have to accommodate and put some type of a drape in here, rubber drape, to keep salts and moisture off of these bearings, these hinge bearings. Sometimes there's like they call it diapering. There's a trough that's built, and the trough is at a pretty steep angle, so it kind of self-flushes itself. There's a few of these around. In the past, to me, so this is an evolution thing with expansion devices. In the past, two main expansion devices were used, one called the steel slide plate, and then the finger joints were pretty common. However, chronic maintenance problems due to leakage, binding, corrosion, collection of free lead are there. Anytime you put steel in the road surface, you're asking for corrosion, right? Steel always wants to get back to its natural state, so it wants to rust, wants to corrode, and just a constant maintenance issue. Here you can see a tremendous amount of patching. Here is a great example of a finger joint. So what's the next question? How many bridges currently have finger joints? 2,000 bridges?
307.
307, okay. Any other guesses? 10 bridges? 20 bridges? So we're really starting to eliminate them. Yeah, that was a good guess, but that was speed, so I'll show you the cheat. So District 7, that's the District 6, I'm sorry, the southeast corner of Minnesota. There's a maintenance supervisor down there, his name is Larry Walensky. Super guy, very knowledgeable about bridges. And we built a new bridge down there, and he wanted the finger joints in that bridge instead of the modulars. And so that was the latest. So this number was going down, but then we added one to it. That was the latest. I don't know, Paul, if you can think of any other bridges that they ask for finger joints. We usually try to get them out of there.
Right. With the diaper system to control the water, I think they've become better.
Yeah.
With the modular, that's the way we've gone.
Modulars, yeah. And they're not cheap, but they work really well. We'll see a picture of one coming up here. So this is the, what I just showed you, the steel flex with the SSA2, the most common, and then this would be a modular. So we have these center beams, and then we have the two side pieces, and there's a whole system of springs and cushions, etc. in these boxes, so that it allows for each of these little bays to open and close at the same time. So not just one is doing all the work, but they work together. Again, in some really long bridges, 35 W, Lexington Avenue Bridge, St. Croix River Crossing, Wabasha Bridge. I'm suspecting that the new what's the new bridge? Blatnick.
Blatnick will have several.
Blatnick will have several. Yeah. And there's some new bridges up in the TPI project up in Duluth that have modulars as well. You see this little minimum shipping length, 70 feet? We never had that in the spec till a couple of years ago. So we had a contractor say that we can't ship what you're telling us to build. So we got into this big thing about how you ship a 35 footer and a 35 footer. Now you got to splice them on the field, and we had them put together a weld procedure. And our structural metals people actually visited the site and watched them weld these things together. Usually they come out of the shop all pre-loaded with glands. You know, these yellow things are gonna come off once they set them in place. So anyway, so we had to put something in the spec to say that if it's longer than 70 feet, then there's got to be a splice in it. So our fabrication methods engineer, their group watches that really close. And so now we know that 70 feet is the max. When was the first strip seal expansion joint used in Minnesota? Jason?
1974.
Thank you. All right, this was it right here. So like I said, this has evolved. These different lobes and different glands, different pieces of steel have changed over time. You can see 1974 to 1970, approximately 540 bridges. The fabrication methods group in the bridge office keeps really good tabs on this. And we have some suppliers that will actually make these glands for us if maintenance needs to replace one. They'll be able to extrude it. They still have the molds. So we have I put together a panel, like, I don't know if I have a picture of it or not, but I put together a panel. We still have it in the bridge office. Tom Merritt was our fab methods engineer, and he had this big filing cabinet, and he had, we call it the gosh wow drawer, right? So you go in there and pull stuff out, and he'd like to show and tell. And so one Friday after he left work, I went into his gosh wow drawer and I took all of these pieces of glands, you know, and stuff like this, and I took it home and I sliced it 3/4 of an inch, sliced this, painted them up, glued them on this big board, and he was so proud he'd carry that thing around meetings and stuff. So it's a great example of all the different glands we use. So how does an engineer determine the need for an expansion system? For a simple single span, it's usually fixed on the lower end. So like I said though, we have some bridges that move uphill, but typically that would be fixed and then you'd expect it to move up. Again, typically, right, generally speaking. 2-span structures fixed at the pier. We talked about that. And a 3-span, they really literally have to investigate that stiffness of the structure, and they'll figure that out. So, no hard and fast rules. Some theory and investigation that they have to do. The number and location of expansion joints is determined based on the maximum joint opening. Typically, we're looking at the 4 inches on each end of the bridge, unless we're looking at one of these big bridges. Then all bets are off. When joints exceed 4 inches, we can provide a modular. We can provide additional joints at the piers to split this superstructure into segments. So, like those 2 bridges by the airport, 92 or 9217 east and west of 494, those have multiple expansion joints. Can't remember how many, maybe a dozen. As you're going across the bridge, next time you drive it, listen for them. Boom, 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 like that. Okay? They're doing a big rehab on that, on those 2 bridges. I think this coming summer will be the end of it. But it's just such a big bridge, we had no choice but to put joints. So in the past, we used to put scuppers, right? So a scupper is just a drain tube in the gutter line that drains right out into the water or wherever it wants to drain. And hydraulics told us a few years back that we can't do that anymore. So we have to try to build our structures with enough vertical curve in them to make sure that the salts and stuff, we try to get it off of the bridge onto the land instead of dropping it in the water. So you'll see a lot less. Well, you guys won't. You can probably notice the difference, but we have bridges, a lot of bridges with a lot of scuppers. Try not to do that anymore. Okay, where did we find this information? So a few years back, everything used to be in 2402. In 2402, I believe, is titled steel construction, steel bridge construction. And then 4 or 5 years ago, we migrated into, we figured that expansion joints, the single gland and the modular had enough of their own information that they should have their own section of the spectrum. So we switched over to 2473. That's where you find the information. And this is what it looks like on that page. Watertight expansion joint device consisting of formed, non-reinforced strip seal that is mechanically locked into the structure. Okay? And then when it gets to the railings, what does it do? The barriers, it turns up. So that we're trying to keep all of that nasty stuff that's on the bridge, so that it goes off onto the approaches, not into the water or below. Okay? Yeah, and in that section in the spec book, there's single joint device and there the modulars in there as well. If we're going to use a finger joint, I think we're going to write a special provision for that. Okay. Yeah, so let's take a look at the bridge plans and then some standards. Lots and lots and lots of detail. So this is a raw standard sheet right when the designer gets it. And then they have to, anytime you won't see these little bubbles like this because this will all be deleted. This will all be deleted when they're done with it. But this is notes to the designer. So this particular note here, we're trying to tell them how far below the road surface is the top of this joint. So from this point here to the top of the road surface, we're trying to tell them the depth here. So the depth might change if the bridge is at a skew and we have to put snowplow straps on top of these. So we put a steel strap across the top. So when the snowplow comes along, the snowplow just continues to ride right over the top. If that snowplow strap wasn't there, then that plow blade has a tendency to drop into that. And it really makes a mess out of the plow and the driver and the bridge. So that's what this is about. Sometimes we plane our bridges, so we would, for noise reasons, so we would finish the deck and then this big planer would come longitudinally and drive down the bridge and remove a certain thickness and level it out. So depends on if we have if we have a snowplow strap or if we have that planing going on. That's what this table's all about. And they're going to put a number in here, and that's what you have to assure when they do the dry run. When that machine comes over the end of the bridge, you want to be there, and you want to make sure that it's that 3/4 or 7/8 of an inch or whatever. Not like this, and not like this. It has to be just right. And we have them that are like this. The St. Peter Bridge, 169 over the river, that had there was an error. Something happened during anyway, the whole story behind that. We won't get into that. That was a bad scene. Ton of information on here about expansion joint devices. This is a detail here, very, very detailed. These little angles will come welded already onto the strip steel, and then this is the snowplow plate, and that will be welded in the field. And there's a very specific weld procedure. There's also some information in here about what they have to use and how they have to prep that and how they have to weld that. The biggest thing is that the rubber gland will already be in there when they lay that steel strap on top. And so they have to, there's the expansion device right underneath here. So they usually will fill that with like some wet sand or something to prevent the weld splatter and stuff from wrecking that gland, rubber gland. Super important, what you see here are the wheel tracks. This is where cars should be driving typically. We try to keep those snowplow straps out of the wheel tracks. We found really early on that if we had one in here, the slap from semis or whatever would bust those pretty quickly. So that's what that's all about. Some more information here. Some of these dimensions have changed. So the first plow strap is 1 foot off the gutter, and then we have maximum spacing. But we'll try to lay this out for you. So it's not as simple. You just got to make sure that the contractor's following the plan. Okay. We put snowplow straps on when we have a skew angle of over 15 and less than 50. So the plow blade won't turn, won't catch if it's less than 50.
Are they not fixed on both sides so they can expand, right?
Correct. Yep, exactly right. This weld only happens on one side. So you can see the weld right here. This little flag on a weld symbol means that it's a field weld. You can see it right here, field weld here, and then this side slides. Good observation. More of the standard sheet information. If there's ADA, which we're really cognizant of nowadays, make sure that they build that according to this standard. We had to go in and take stuff out. When I was here on Wednesday, my supervisor, Paul Pilarski, was here, and I mentioned that the contractor was using too big of a jackhammer, and he busted out, spalled out the bottom of the deck, and it fell through the sunroof of that lady's car. That's what they were fixing. They were fixing a bridge that wasn't built properly. So they had to go back and erode some concrete out and recast that so that it met the ADA. Super important. Super important. Okay? All right. So I just want to show, there's that turn up, right? It goes up into so that everything stays in the gutter. So this might be a sidewalk right here, and then we have a traffic barrier, and then back out onto the bridge, driving surface here. But in each barrier we have turn-ups. If we have a sidewalk, it's just going to be a little bit longer, but it's still going to be there. Okay? And that gland is going all the way through. The gland is coming all the way up. It's going to stick about an inch above the end of that extreme. Okay? When they're setting these expansion devices, so here we have a center median, a roadway surface, a traffic barrier, a sidewalk, etc. We have elevations, and the people that are putting those expansion devices in, I think, do a really good job. They're shooting those elevations all the time and making sure that they're correct. So this would be the bridge coming across, and then it hits the abutment. There's the bearing, and then sometimes we have conduits in here. So there's our expansion joint. So the bridge can open and close this way. This is pretty static, right? And the bridge can go up or down. So if we need to jack it, we can lift the bridge up. So for that reason, we have to put expansion deflection joints. So they expand and deflect so that the conduit doesn't break, right? The conduit has to be able to do the same thing that the bridge is doing. So you'll see those. It's kind of all things expansion today, right? It's gonna go forward into the concrete, and usually especially for the deflection, it's just gonna be a big rubber tube so that it can do this, and they put like shrink wrap, bubble wrap, something, whatever they each have different things to create that void around that deflection. Okay? Here's a good picture of what that looks like. So this is a sleeve, and the conduit goes inside of this, so this can go back and forth, and then that's the big deflection. And everything it's grounded, right? Everything is grounded, so there's jumper wires inside. But that's the void I was talking about right here, around this deflection rubber, so that it can go up or down. So again, if we're going to jack the bridge, we have to know that that's in there, or we're going to tear something apart. Okay, so shop drawing review. We, in the bridge office, the designers put together the sheets, pretty generic looking. Then they go to a fabricator, who's an approved fabricator, and they have to draw up their own shop drawings, which are super detailed. And then those shop drawings come back into the bridge office, into the Fab Methods unit, and they look through them to ensure that everything is correct. Okay, and that's just where it's spelled out of where they have to send them and stuff like that for review. Local projects, cities and counties, they can choose to defer that to a consultant, or some cities are big enough where they can do it in-house. Minneapolis, they have their own bridge crew, bridge team. But for all MnDOT jobs, they come into the bridge office to the Fab Method. So this was Ironworks. They do a fantastic job. I asked them if I could show their shop drawings in class. They said absolutely. So again, what's the little flag mean? Field weld. So this device is going to come out. There's a crown break right there. That's the center of the bridge. That's a crown. So they'll put everything into those right elevations and the field weld that. Okay. Here's the plow strap detail. There's the gland. Minnesota requires a 1/4-inch gland. Most states require 3/16. So we're unique in that area, but we found that 1/4 inch is better. So that's something you're going to look for. We had one modular joint come out for the Bloomington Ferry Bridge, and the inspector saw it got offloaded off the truck, and he looked at it, and he could tell just from a distance that those glands didn't seem thick enough. And so he called the bridge office, he called me, and he said, I think I got an issue out here. I kind of put my tape measure, and they don't look thick enough. And so I grabbed Jisha Lin, who's our Fab Methods engineer, took a little field trip out there, and sure enough, it was built by D.S. Brown, and they had used the wrong gland. So just that little thickness, that inspector could pick that up. And we also had some issues with the rails in that modular. They have to be within a tolerance, like an 1/8 inch and 10 feet type of thing. They weren't adjusted, they weren't bent back into straightness once they pulled it out of the hot dip galvanized. So we had two things going on. Remember that whole fiasco, Paul? Anyway, more shop drawing review. I gotta watch my time here. Here's the cover plate that I was talking about. So they put that in here too. This is super detailed of what has to happen in the shop. There's the material list, and our Fab Methods engineer, his team will review. So they review this for general compliance with plans and specifications, and then we have it was Ed Ludkin, who's our current state bridge engineer. He was the bridge construction and maintenance engineer. Right now it's Andrew Lauber. So they stamp each sheet with that. So what does general compliance mean? That means that we're not necessarily we're not approving, we're saying that, yes, it looks correct with our little cursory review that we do in the office. So we're not taking on any liability for these things being wrong. So that's what our lawyers told us that we needed to have in, okay? I'm telling you a lot of information you don't really need to know, but it's kind of fun to know. So here's the detail for the turn-up, and that we have to make sure that that's all built correctly when you're out in the field, okay? Here's that big steel anchor that this little strip gets welded into, and this is what locks it into the abutment and also on each side into the deck. I'll back up one here. Here's the little angle, you know what we're talking about? So this is the side where it's going to get welded, the plow strap's going to get welded on, and this is the side that it's going to slide on. So those are all, there's some raw material right there, stock that the fabricator has. And then this is what it looks like after they get it welded. You can see they chamfer these edges. So this is going to be butted together and field welded. So you can see that's all prepped. But now where this thing ends up going is it goes into the hot dip galvanizer. So we have two sections in the spec book, 3392 and 3394. One is 3392 is for small items like nuts, bolts, washers. 3394 covers most everything else, minor components, we call them. Expansion devices will be covered by this. So they have to, in that section, it'll call out a certain ASTM, like I think it's A123 or something, that the galvanizer has to follow to galvanize our products. Okay, so this is at the galvanizer. This is actually Zulk, one of the bigger galvanizers. You can see right here, hydrochloric acid bath. I think it's about 10 to 15% acid. So they dip it, they dip the steel in, and that takes off everything that's not supposed to be on there. Sometimes it'll take the mill scale off, it'll take any oils or greases, just super cleans so they take it from that, they dip it into a couple tanks to neutralize that, and then they just take it right over into the vat of zinc. So this tank is 60 feet long, and I think it's about 8 feet deep, and I think it's about 10 feet wide. So it's molten zinc. Things go in. Depends on the thickest piece of steel on that piece that's being dipped. So if the thickest piece of steel is 3/4 of an inch, the person who's dipping that knows that they have to leave it in there for 5 minutes, 6 minutes, or whatever. If it's 1/4 inch steel, they leave it in there less time. Okay? But they always go by the thickest piece of steel because the zinc is actually melting together with the ferrous metal. Okay? I think I got a slide about this. Everything comes out at an angle so that it self-drains. Typically, if there's moisture on anything, that's why you see all this splatter. You see splatter all over the place, so you don't want to be near this thing unless you're protected like that guy is. Because it'll blow. It'll just, steam will just poof, you know, and yeah, it goes up to the ceiling. And they also have to make sure that there are no seal welded tubes. So that means that there's no vent holes. So the vent holes have to be pretty big. So if you trap moisture inside that tube, boom, right, the whole thing's gonna blow. So they're very, very careful in that area. It's a neat tour, it really is. So this is what it's going to look like. This is the hot dip galvanized. Here's the snow plow. strap. Again, this is the side that's going to get welded on. So the contractor is going to have to grind this galvanizing off before they weld that strap on. Okay, that's what it looks like. Again, just some general trivia, just for your knowledge. Here's the steel that we're coating, and when they put it into the zinc, it's going to melt into the steel. So this particular layer is called the gamma. It's about 75% zinc, 25% metal, right? This layer. There's another layer called the delta, the zeta, and then the eta is 100% zinc. So when they're grinding, you want to see when they're grinding that they start to get sparks off of their grinder. Okay? And then when they're welding, if it foams and it looks porous, that means there's still too much zinc in there. Okay, so if the weld looks wrong, it probably is. And we want these snowplow straps, we want them welded on there correctly, or else our maintenance people are coming out in the fall and having to do a lot of extra work. Okay, so they're not just grinding a little layer of zinc off, they're literally grinding down, and we're talking 4 to 5 mils of galvanizing. Okay? That's pretty neat. That's the beauty of hot dip galvanizing. It actually melts in, it's not a topical coating, it actually melts into the steel. Lots of different things. I mean, they galvanize lots of different things. It lasts for a very, very long time. So question, how hot does that zinc bath have to be? It's right around 840 degrees. Structural metals inspectors. So we have a team of four people in the bridge office that go from fab shop to fab shop on a regular basis, and they are constantly testing for thicknesses. So they would go to a shop that's fabricating the steel to look at the welds and make measurements and collect x-rays if they're building like a steel girder. The contractor mostly has their own quality control that they have to follow, and then our group does the quality assurance, is what you guys will be doing. So you look at their results and you assure that everything is correct. But they will take spot measurements on, they have the instrument that can measure the thickness. So our ornamental railings are hot dip galvanized, and then they're powder coated on top of that. And they have an instrument that can measure the thickness of the galvanizing and the thickness of the powder coating. And both have to be a certain thickness. So they're constantly giving inspection tags, etc., for anything steel. So let's head out to the construction site. Typically how you'll see it come out, there's some backer rod stuffed in here so that when this is put into the deck and the concrete is poured, that those openings where the gland goes don't get all jammed up full of concrete, but that's how they'll come out. The gland will be wrapped, and there'll be some containers of some different pieces in here, or maybe the lube adhesive that's used to put the gland into the steel. The modular will come out like this. Happens to be one of the modulars that is going to have to get spliced. So you can see how they prepped. So this has to be a full pen weld, full penetration weld. So they'll weld on this side, they'll weld on this side, and as the two come together, right? And they have to fill that in so that it's the same thickness as the rest of the rail. So very, very, and all that galvanizing has to be ground out here. You can never weld in galvanizing. They're pretty good about it, but it's something to watch. So typically we do not allow any welding of really anything on a job except for the expansion joints. But it's so critical to get this joint set at the right elevation, the crowns, that we do allow some tack welding. We'll allow them to tack weld to our reinforcement bars. And here you can see they have an adjustment rod. They put a PVC cup down here at the bottom of the concrete form. But we do allow a certain amount of welding to lock it into that spot. These little steel plates are just tack welded on one side, and they're there to keep that opening at the right opening. So you'll see a picture. So this is the abutment, that's the bridge. When they get probably about 10 feet out during their concrete deck pour, you'll see the foreman of the deck pour, he'll walk along that expansion device with a crowbar and he'll pop those off. So now so the bridge is crowned, right, before we put the concrete on it. And then as we put the concrete on it, it comes down, that residual camber comes out. So it starts to flatten. Well, you can see if we got this expansion joint welded tight with these plates, it's not going to move. So we start to get out there, and then so he pops that plate off there. So now that bridge side can start to rotate with the beams in the bridge as it's getting loaded. Okay, right here you'll see that's a median barrier, or it's a median itself, in itself. There's the little plates. They just hold the extrusion in place until the deck is being poured. Here you can see you're coming across, and there's a gutter line right there, and then you're going up through into the median, and then back down again and across. Pretty detailed work, like I mentioned earlier. They got the surveyor out here. They're shooting, making sure that everything is where it's supposed to be. Inspectors, we got 2 MnDOT inspectors saying, we think we saw a problem over here, let's look at the plan. So you're talking to the foreman again. String lines they're perfect. They work really well. So here you can see a string line being attached right here. A little bit of tack welding we allow. Yeah, a lot going on here in this picture. So I think I mentioned this on Wednesday that we want, just before the deck pour, you're going to want to walk out here. You're going to walk across. You want to make sure there's no tie wires laying down in here, no paper tags, no nothing, right? Because what you see down there now is what you're going to get after the deck pour. Typically, the contractor will put some 4-inch wide duct tape over the top of that joint just before they pour this. We want to make sure that they're vibrating really good in this area. We want to make sure we get good consolidation underneath and around that joint. So yeah, we got a shop vac out there because there was a little too much debris down in there that we needed out. Here you can see they're starting the deck pour, and you can see the gentleman here with the vibrator making sure we have great consolidation. It's the right height here. And then you can see here's our foreman, and he's walking along popping these joint plates off of there. 3 most important inspection details: setting of the opening for temperature. That'll be told what that needs to be in the plan. The top elevation. Again, when they do the dry run, you'll be observing that to make sure that they're the right height, and to make sure that the gland is tucked in afterwards. They have some really good tools now, so you don't typically have a problem. So once the bridge gets a little bit older, sometimes this gland will rip or tear for some reason. So they came in and took the cover plate off, the pedestrian sidewalk, and now they're just about to put a new gland in this one. Here's a modular. You can see that we have these huge cover plates that go up and over the top of the barrier, so that when snow plows or whatever are coming through here. We can't have an opening bigger than 2 inches or it becomes a snag hazard for a vehicle. So say a car hits and the hood catches in that 3-inch opening, that hood could grab and it basically comes off the car and it comes through the cab of the car. So we're very, very sensitive to our openings in our barriers and railings. This is just the detail again for the snowplow strap. Here you can see this is the wear part. So this is galvanized. It's still kind of on there, and the galvanizing is kind of wore off from the tires. But you can see that those snowplow straps were too close to the tire slab. So the maintenance came out, and that's all that was left of them, and put some new ones over here. So super, super important. At the end of the day, 3/8-inch snowplows be recessed about a 1/4 of an inch below the top of the road surface. There's the table that our designers have to use, but in the note on that sheet, it'll tell you what distance below the proposed driving surface it has to be. Okay, they beat that to death enough? Here's a good looking snowplow strap. So welding, they're gonna weld one pass, weld the second, weld the third, come back over here once it cools, back and forth 3 times. There again is snowplow straps snapping off. This welder right here, he's standing leaning against the barrier because I just told him that he was upset with me because I just told him that he put him on wrong, and he was kind of trying to figure out what he was supposed to do now. The problem that he had is he didn't move these over far enough to weld them on, and so if this thing were to completely close up, this snowplow strap would have hit this one, and it would have just snapped it right off. So he put them on wrong. Well, luckily we caught it pretty early on. I shouldn't have said that I told him he did it wrong. I was standing with the inspector. I never direct anybody. I give my directions to the inspector. The inspector then talks to the foreman, and they fix it. So in that case, I meant to say that I saw it being a problem, and I told the inspector, and he told me that he had to fix it. So that's what it looks like behind the cover plate. There's that turn-up area. Again, we want everything to stay in this gutter. Very important that the contractor cuts that gland off 1 inch above the steel, and it has to be horizontal. Okay, 1 inch above the steel, and that's in the plan for them to do it that way. There it is, right there. Cut the gland horizontal, because what that does is it keeps, we could have water come all the way up to the top of that before it goes over the top. So we were finding that the contractors were putting this in. That's the reason we put this detail B in, is because they were sometimes leaving the gland way down here. So again, we just started to see it, so we got to put a stop to it. Already talked about that. There's an example right there of the plate being put in backwards. Okay, traffic flow was going this way, the expansion was happening over here. So that's not a cheap fix for a contractor.
You knocked all that out and re-poured all the stuff.
Yeah, so what they have to do, these are fixed anchors right here. So they had to come over here and they had to put new anchors in, new anchor in, and another new anchor in. So they have to drill, and usually we have some super good adhesives. So we drill the hole, clean the hole, and put those adhesives in there and stuff that anchorage assembly in there. So anytime you do a redo, We don't like that, but there's always an option to fix it. How long do we expect these to last? Typically around 20 years, and then if we have a modular, again, they're pretty expensive. 40 years is kind of the goal that we're looking for. Some last shorter, some last longer. Bridge maintenance takes over once the bridge is open. If you're out doing inspection and you walk underneath the bridge and you see all this sand, well, it wasn't from a mole, right? It was from the expansion joint gland up above here leaking. And this can be very detrimental to our bearings and the ends of our beams. So it's super important that this is caught and that maintenance gets out there and they either put a patch, or sometimes they have to re-gland, or sometimes maybe we'll write a contract for multiple bridges. So there's a sign right there, right? That's not because that's where the tire's going across. That's because there's a hole in that gland and it's just leaking right through. Okay? There's some different products out there. Belzona is a pretty popular product that they like to use. So they kind of clean everything up, put some adhesive in there, and put some more rubber gland in. They do this now and then. There's the Belzona right there. Oh, here's I forgot I had this in here, sorry. So there's the first gland, 1974. And you can see how it evolved. The problems with these is the lobes weren't in tight enough. So you get this full of sand, incompressible stuff, and then, or ice or whatever, and then a semi would drive across and pop it. And then it would pop the glands out right up here. So you can see some of these lasted a little longer. That's 243 bridges. This one was junk. This was made of like 1/4-inch steel and it bent. So we only had 66 bridges in a couple years, 163. The Watson Bowman, that was one of the better ones as well. This was a really good one too, I thought. And then, here we're today, 1993, and I can't show you anything new after that because this one's working. The SSA2 gland is working really, really good. It's held in here really nice. These are the modulars I was talking about. So this is DS Brown. This is the Watson Bowman, Acme. This is the Steelflex with the L2 400 gland modular. There's an APL for this. That's the lube adhesive that goes in there. In the past, there was every type of tool, whatever somebody could bend up on metal to assist in getting these things installed. Stay away from this when they're doing this because it's just super, super messy. And if you get it on you, it literally has to wear off. It's kind of like getting super glue or something on your hands. But yeah, don't get too close to that. This is the newest tool. It's just a pneumatic gun with a chisel point that's blunted on the end. And they can literally just ride this thing right along here and just rattle that right in. Super fast. So most everybody has gone to this. If we have to go back out there, maintenance, these pictures are just showing different ways to clean that, get that out of there, sandblasting, torch, grinders, however they have to remove the adhesive, but it needs to be cleaned before they install. Here's a picture of what maintenance might do. This needed a new gland. So they brought the gland out, took the cover plate off, stripped everything out, and then they were reinstalling. Reasons for replacement, sometimes, like I said, the fixity part, bridge is supposed to move one way or the other, theoretically. If it doesn't, maybe it moves all one way instead of both ways. This is what's going to happen. And our regional bridge construction engineers, and what Paul used to be, they would go out and they would reviewed this with district people, and they would say, yep, this is at its max, we're gonna have to, you can see the plow straps are almost off. So this is too wide, so we'll tear that out. This is too tight. So here's an example of a replacement for this. They come in and they saw cut a certain distance, usually a foot, foot and a half. They use some hammers. They have to be extra careful when they do this. So if you're on this job and they bring out this big jackhammer, remember the ends of the beams are right here. We've had jobs where they bring a big chipper in and boom, they knock the whole end of the beam off. So you can see it down in here. There's some destruction of the end of the beam. This is what we like, these 15 to 30 pound hammers. For doing this removal, they straighten the rebar. Sometimes they have to, if it's epoxy coated, they have to recoat. Maybe they have to put some more rebar in here. Looks pretty clean now. Setting the joint in. They put some spanners across here. They set it to the right opening, 2 inches typically. And getting ready to pour the concrete. Goes pretty smooth. Got our plates in here for snowplow straps. And here's the finished product. Back together again. In the spring, we do our maintenance crews go out and they try to flush every bridge. So that's the cleaning part, repairing and placing the gland, establishing and replacing the joint if it's too wide, too narrow. Repair the steel extrusion. Welding the plow straps back on is, some bridges it's annual. You can name a few. So they know that the bridge is moving, it's bouncing, and there's fatigue on that plow strap and it snaps off. So in the fall, right before winter, they're out there putting new straps on. And there's always some spalling going on that needs service. That's it. I'm 2 minutes ahead of schedule, so any questions on expansion devices or?
I've seen the joint replacement jobs. That's the worst place contractors have a hard time getting cleaned out. They want to always just blow it out and not vacuum it, and a lot of times it goes down quite a ways, and it just swirls down there, garbage.
Yep.
And they most of the times will refuse to bring out a vacuum to back it up. I don't know why. They just fight.
Gotta be on them, right? You gotta be there. You gotta be observing.
I brought them the little nozzle, the real thin one,
Yep.
way down in there, and the adapter so they could actually use it.
Yep.
Otherwise, they weren't getting garbage out of it.
Yeah. It's important. All things that they have to do. So. All I had for expansion.
Any other questions for Mark?
Take my plans and go home.
So we'll take about an 11-minute break, 25 after we'll reconvene.
Just makes sense.